So let's begin by talking about extreme values. And now again, extreme values are going to be the central player in our applications for the derivative over an interval, specifically when we look at optimization. So there's actually going to be two types of extreme values that we're going to look at, absolute and local. So first we're going to define absolute extrema. So let's say f of x is a function with domain d of f. Okay, so recall that this d of f is just the natural domain of f. Now, it could be the case that we're also looking at a domain restriction of f, but for now, let's just say that the domain of the function we're looking at is this d of f. Okay, so whatever it is. Then if there is a point C in the domain of f such that if we look at f of c, and f of c is greater than or equal to f of x for all x in the domain of f. So basically what I'm doing is I'm looking at all points in the domain of f and just comparing them and finding the largest one, finding the largest number in the range of f. Then f of c is the absolute maximum. Of f. Okay, so pretty straightforward definition. If I find a value in the range of f that's bigger than all the other values, that value is the absolute maximum. So looking over the entire domain of the function. So just some more terminology. In this case, the absolute maximum is said to occur at x equals c. Okay, so there's a really subtle difference that we'll kind of get into here, because in problems and applications, it'll say find the absolute maximum. Now what that means is to find the actual y value, so the value in the range. But a question may also say find where the absolute maximum occurs. Now that's the point in the domain of f. And now it may also be the case that there are more than one x value in the domain for which the maximum occurs, and that's perfectly fine. But when we have an absolute maximum, that y value is unique. So that is the unique y value that is the absolute maximum, even if it occurs at more than one x value. And so we don't want to leave off minimums as well, but I'm just going to make a note. So we can define the absolute minimum similarly. And so what do I mean by that? Well, what's the only thing we need to change? Well, if the absolute maximum is the function value that's larger than all the other function values, well, the absolute minimum is going to be the function value that's smaller than all the other function values. So all we need to do is switch to less than or equal to in our definition, and that's it. So pretty simple definition, but it's going to play a big role later on in this topic. So absolute maximum, absolute minimum, and then the x values in the domain where the absolute maximum and absolute minimum occur. So just get used to this terminology. We're going to be really precise with it. It takes a little bit of time to get used to, but this first lecture there's going to be a lot of terminology to just nail down. So we just need to go through it. But first of all, before we get into more terminology, let's actually look at a graph and see what we're really looking at here. All right, so here we have three functions, f of x, g of x, and h of x in blue, red, and orange. And so looking at the graphs of these functions, we just want to identify, first of all, what are the absolute maximum, what is the absolute minimum, and then where do those points occur. So first things first, so for f of x, so the absolute max, so I'm just going to abbreviate absolute max as ABS max, is what? So we look and we say, what's the largest y value? So the largest value in the range of f. Well, it looks like it's 2. So the absolute max of f is 2. And it occurs so where does the absolute max of f occur? Well, for what x values does f of x equal to? Well, it looks like we actually have 2. So at -2, f of -2, f of x is 2. And then at x equals 2. So it looks like the absolute max occurs at x equals plus or minus 2. So again, we're seeing that even though there is one absolute max of 2, that's the highest point, it can occur at more than one point. So it occurs at 2 and -2. So what about the absolute min of f of x? So I'll just abbreviate that, ABS min. Well, we just look, what's the lowest value that f attains? It looks like it's 0. So the absolute min of f is 0, and it occurs this time only at one x value. So it occurs at x equals 0. Alrighty. So now let's move on to g of x. So what about g of x? What is the absolute max of g of x? I'll give you a second to think about it. Okay, yeah, so you should have said 1. So we just look, what's the highest value that we reach? Well, we reach 1 here. Here we go all the way up to 1. Here we go all the way up to 1. So the absolute max is 1. And then where does the absolute max occur? Well, it occurs in 3 places, right? So it occurs at -2, 0, and x equals 2. So 2, 0, and -2 is where the absolute max of g occurs. And then finally, for G, we have the absolute min. So the absolute min of G looks like it is down here at -1. So again, we're looking for the y values. Now where the min occurs, we're looking for the x values. And let's see, where does the graph of G equal -1? At x equals -1 and x equals 1, so plus or minus 1. Okay, so now let's look at h of x. What is the absolute max of h of x? Well, hopefully you're getting the hang of it. It's not too hard just looking at the graph. It looks like the absolute max is 0. And where does it occur? It occurs at x equals -2. At x equals -2, h of -2 is 0, and that's the largest function value over this domain right here. Okay, so the absolute min we can do similarly. Looks like the absolute min is -2, and it occurs at x equals 2. Okay, so hopefully this graph has helped you see what an absolute max is, what an absolute min is. It's pretty easy to pick them out and where they occur from the graph of a function. Now what we want to work towards, and it's going to take a little bit of time to build it up, we want to figure out how to find the absolute max and min of functions just by looking at the definition of the function without graphing it. So that's really cool, and that's where the calculus is going to come in, looking at the derivative over certain intervals. Okay, so we want to bring up a very important point here. So we just looked at 3 examples where we found the absolute max and absolute min. But there's a glaring question we need to ask about functions. Does every function have an absolute max and or an absolute min? And of course the answer is no. And here we have 3 examples of functions that either don't have an absolute max or min, only have an absolute max and no min, or only have a min and no max. Okay, so let's dive into this a little bit. So let's look first at f of t. And now what I want you to notice is that the domain of all of these functions is 0, not including 0, to infinity. That's the domain that we're taking for these functions. And let's see, so f of t. Is there an absolute max for f of t? Well, let's look. I'm going over here, and I would say that it looks like maybe y equals 1 is an absolute max, but I never actually reach y equals 1. So I get to 0.9, 0.99, 0.999, 0.9999999, but I never reach 1. And there's another problem anyway. If I look over here, I actually have function values on this side that get higher than 1. And they get larger and larger and larger and larger. But there's no single y value that's larger than any others. If I say, okay, f of 3 is 4, that's the absolute max. Well, no, because f is going to keep increasing. And if f is really going off to infinity like it looks like, there's going to be no absolute max. So f has no absolute max. But now it does look like f has an absolute min or an absolute min of 0. And then at x equals 1. Okay, so f is an example of a function that has no absolute max because it increases without bound, but it does have an absolute min. So how about g of t? Well, g of t goes up right here, reaches 3, and it doesn't look like it ever goes above 3. So we can conclude that the absolute max of g equals 3, occurring at, well, looks like this is 0.25. So at x equals 1/4, or 0.25. But similarly to f, g does not have an absolute min. So if we look, here's the absolute max. We're leveling off here, and it doesn't look like as t goes to infinity, g is ever going to get below -1 or ever even reach -1. So it looks like we have a horizontal asymptote at y equals -1. But then if we look over here, you say, okay, well, we're approaching -1 from the right? So the limit of g as t approaches 0 from the right is -1, but we never actually reach -1. And that's very important for having an absolute min or an absolute max. We actually need to reach that value. We actually need f of 0 to exist, but here it does not. F of 0 is undefined. We have a hole at t equals 0. So even though we're getting closer and closer and closer to y equals -1, we're never reaching it. There's never one single y value that the function reaches that's smaller than all other y values. And we'll see that that's actually a phenomenon that's happening because this is an open interval. That can't happen for a closed interval. So no absolute min for g. Then finally, for h of t, it looks like we have the same problem at t equals 0. We never quite reach t equals 0. And then we're just decreasing kind of indefinitely. So it doesn't appear we're ever going to reach an absolute minimum value either. So h of t has no absolute max or absolute min. Okay, so we see some very important examples here. So a function can have an absolute max and an absolute min. It can have an absolute max but no absolute min. It can have an absolute min but no absolute max. Or it can have neither an absolute max or an absolute min. And really, whether or not a function has an absolute max or min, that we'll really dive into this point later, depends on, first and foremost, the function, but it also depends on the domain that the function is defined on. Okay, so I told you that there were two types of extreme values we needed to talk about. So we've talked about absolute extrema, absolute maximums and absolute minimums. They may or may not exist. Okay, so the next thing we need to talk about is local extrema. So the idea of a local maximum or a local minimum. So let's see what that is. So f of x is again going to be a function with a domain. Okay, so for absolute extrema, we had to look over the entire domain. But for local extrema, we actually are only going to look in a small interval around a point. So if there is an interval, an open interval, let's say AB, contained, so a subset of the domain of F, such that there is a point C in this open interval for which f of C is greater than or equal to f of x, not for all x in the domain of F, but just for all x in this interval. Then f of C is called a local maximum. And then, kind of borrowing the same terminology, we say occurring at x equals C. So the local maximum is the actual function value, but it occurs at the point in the domain. And then, of course, we'll make the note, similarly, define local minimum. And the only thing we need to change is, of course, that f of C is less than or equal to f of x for all x in this open interval AB. So this seems a little bit strange, and it's very technical, this definition. But what it's saying is really simple. It's just saying that if I zoom in around a point far enough, that point looks like an absolute extrema. It looks like a maximum. Or in other words, it looks like the top of a hill or the bottom of a valley, locally. Okay, but it may or may not be an absolute extrema. And that's a very important note I just want to say, that local extrema may or may not be absolute extrema. So just like with absolute extrema, I think if we look at the graph of a function and point out some local extrema, you're going to understand exactly what's going on here. And you really don't need to kind of wrap your head or beat your head against this kind of technical definition again, but this is just to make it precise, but let's get a lot of intuition by just looking at a graph. Okay, so plotted on this graph is the function x cubed minus 3x. Now we're not going to worry about this function right now, but what we want to do is just talk about the local maxima and local minima. So look at x equals -1. And here's what I want you to do. I want you to just zoom in right here. So if I look at -1, kind of in this small open interval, now notice I'm kind of cutting off other parts of the function. I don't care what's happening far away from -1. I only care about what's happening near x equals -1. I guess this is really supposed to be x. That's a little typo. Yeah, okay. But I'm looking near x equals -1. So this looks like the top of a mountain. Or in other words, f of -1 appears to be larger than all function values just to the left and just to the right of -1. So what that means is that f of x has a local max at x equals -1. Okay, so in other words, the local max occurs at x equals -1 because we zoom in and it looks like the top of a mountain. But notice this is not an absolute max. And why do I say that? Because look over here. This is all in the domain of f, all these x values. And if it looks like if I take an x value larger than 2, my function values are actually larger than f of -1, which is equal to 2. So f has a local max, we'll say, of f of -1, which is 2. So the local max is 2. It occurs at x equals -1. But this is not an absolute max because the function gets larger in a different part of the domain. And we can do the same thing for x equals 1. So if we zoom in just in a narrow window around x equals 1, we have that f of x has a local min of -2 this time at, so the local min occurs at x equals 1. And similarly, this is not an absolute min. If we look at x values smaller than -2, our function values are going to be smaller than -2 in the y, along the y-axis. So down here, these function values are smaller than this local min, but that's okay because this is just a local min. I just have to zoom in close enough so that it looks like the bottom of a valley. Okay, so hopefully you're starting to understand the distinction between a local max, local min, and an absolute max and an absolute min. Okay, so I hope you hung with me, and I hope you're starting to get the picture of what an absolute extrema is and what a local extrema is. But here's the crucial question, and this is where we're going to have to bring in calculus. So given a function, how do we find local or absolute extrema? So how do we find the absolute max? How do we find the absolute min? How do we find local maxima and local minima? Because as you know, when we're given a function, very rarely we're not given the graph. Okay, and you may know what the graph looks like for some simple functions, but for a complicated function, you're kind of out of luck. I mean, just given the function. I mean, you can graph it. If you graph it, you can probably answer some of these questions. But, you know, the ability to graph a function is a relatively new phenomenon, right? So we didn't have graphing calculators years and years and years ago. So the point of what we're doing is to think, how do we actually figure out kind of the shape of these functions and where these local extrema or absolute extrema occur? Well, there's a very important observation with the derivative. So here we go. Key observation that sort of saves our bacon when we're looking at functions and trying to find absolute extrema. If f of x has a local extrema, so maximum or minimum, at x equals c, and here's the key part, here's the calculus, f is differentiable at c, then what's the conclusion? This is going back to something that we've talked about before, and I told you that it's important before. So if f has a local extrema at x equals c and f is differentiable at c, I want you to think about the graph of a local maxima. The local maximum occurs at the top of a mountain, if you look at it. Let's just sketch a graph of a local maxima. So if the function is differentiable and it has a local maxima, what can we say about the tangent line? The tangent line is going to be horizontal. So we can conclude that the slope is 0. Or in other words, if f has a local extrema at a point where f is differentiable, then f prime of c equals 0. Now, before we get ahead of ourselves, this does not mean if the derivative of a function is 0, there is a local extrema. And we'll see two very important counterexamples. But what this does allow us to do is find candidates for local extrema. So if f prime of x is 0, then f is likely to have extrema. At these x values. And so these x values are given a special name. So values of x for which f prime of x is equal to 0 are called critical points. And they're called critical points because they're points that are critical to finding local extrema. So oftentimes the first step in finding extrema, whether that be local or absolute, is to find the critical points of a function. Because if the function has these local extrema and f is differentiable, then you know or in other words, it's necessary that the derivative be 0. Okay, so where do extrema occur? We can sort of narrow this down based on our last conversation. So an extrema will occur at a point where f prime of x is equal to 0, at a point where f prime of x is undefined. So notice that we said that if a function has a local extrema and f is differentiable at c, then f prime of c must be 0. But the same argument can be made if the derivative is undefined. So if it has a local extrema and the function is not differentiable, then of course f prime of that x value will not be defined. And then lastly, the thing we haven't talked about is extrema can also occur on the boundary of a domain. So for instance, the endpoints of an interval. So again, just to make this definition very clear, points in the domain of f for which f prime of x is 0 or f prime of x is undefined are called critical points. So notice we're also including points for which the derivative is undefined, but of course those also have to be points for which those x values are in the domain of f. And these are candidates to be extrema. And we'll see exactly how this works in the example. Okay, but basically the first step is to take the derivative of a function, set it equal to 0, or find where it's undefined, and then later on we'll learn ways to actually test these critical points. And then the only other thing to consider is number 3 here. And you just have to think that it's possible that the extrema are occurring at the boundary of the domain because the derivative isn't going to pick up those points on the boundary of an interval. All right, so I told you that just because an x value is a critical point does not mean that it is a local or absolute extrema. So here are 2 examples. Notice, first of all, f prime of 0 equals 0. And then notice that g prime of 0 is undefined. Okay, so in other words, x equals 0 is a critical point of f, and x equals 0 is a critical point of g. But neither f nor g have extrema at x equals 0. And that's okay. All we knew is that x equals 0 was a candidate for being an extrema. But there are a couple of interesting cases that can happen. So first of all, g has what's called a vertical tangent. right there. Okay, so a vertical tangent, as we know, is just a point where the slope of the tangent line is undefined. Or in other words, the tangent line is vertical, hence the name vertical tangent. And we're not going to talk a lot about this right now, but F here has what's called an inflection point or sometimes called a saddle point. We're not going to be super precise with this terminology, but in different contexts, you call it different things. We're going to talk about inflection points later. So it has an inflection point. I mean, that doesn't mean that it can't be an extrema, but this sort of saddle point where you start to have a maxima, kind of on one side you have a maxima, on one side you have a minima, but of course it's neither. Sometimes called a saddle point because it looks like, it looks like the back of a horse where you would put a saddle. That's where the name comes from. But the point is it's not a local max or min, because to be a local max or min, this y value has to be either larger than everything to the left and right or smaller than everything to the left and to the right. But that's not the case. So again, the point is, just because you have a critical point, a point where the derivative is 0 or undefined, doesn't mean that's an extrema. It just means it's more likely than any other point to be an extrema, or in other words, it's a candidate for being a local extrema. Okay, so the general strategy for finding absolute extrema of functions falls into two camps. There's something called the closed interval method and the open interval method. And we're going to start with the closed interval method. But before we do that, we actually need to discuss something special about closed intervals. So it actually goes back to something we talked about before, way back with continuous functions. So it turns out that continuous functions have a lot of really nice properties. And some of the big theorems that we need to discuss in calculus, such as we've already talked about the intermediate value theorem, depend on a function being continuous. And that's going to come up again here. So the backbone behind the closed interval method is something called the extreme value theorem. So we saw examples of functions that didn't have absolute max and or absolute min. But the extreme value theorem actually comes in and tells us a special case where we know a function will have an absolute max and an absolute min. So here's what it says. If f of x is continuous, so there's that key idea of continuity, sort of as being just like a bare bones necessity for some of these big theorems. If f of x is continuous on a closed interval, say a to b, then f of x has an absolute max and an absolute min. So this is pretty amazing, because we saw these examples where f did not have an absolute max or min, but a lot of those cases were happening because either the function was not continuous or it wasn't defined on a closed interval. And this is saying that if f is continuous on a closed interval, then you are guaranteed to have an absolute max and an absolute min. Then it's just a matter of, well, how do you find them? But with the extreme value theorem, we know exactly where they're going to have to occur. They're either going to have to occur at a critical point, or they're going to have to occur at the endpoints of the interval. The endpoints are the only points that aren't considered by critical points. Critical points can't detect endpoints of intervals. They can only detect, well, points where the function is either 0 or undefined. So now we're ready to discuss the strategy for finding extrema on closed intervals. Okay, so here's the first takeaway from this probably long-winded conversation on extrema in this first lecture. And that's the closed interval method. Okay, so if you didn't follow anything else, pay attention to this. Okay, so if you have a function that's continuous on a closed interval, you have an absolute maximum and an absolute minimum, and you can find them relatively easily. All you do, find the critical points. So step 1 is just to set f prime of x equal to 0, find the critical points contained in the closed interval. Then once you have those critical points, it's so easy. All you do is evaluate the function at the critical points and the endpoints. The largest value of those evaluations is the absolute maximum, and the smallest value is the absolute minimum. Then you are done. Easy as it gets. So methodical. Take the derivative, set it equal to 0, evaluate the function at those critical points. I guess I should also say check where the derivative is undefined. We'll get there. You'll see that in the examples. And then finally, also test the endpoints. The endpoints, the function could also get larger at the endpoints, but you only have 2 points to consider in a closed interval, a and b, and then of course all of the critical points. So that's the closed interval method for finding the absolute maximum and absolute minimum for a continuous function on a closed interval. You will always find an absolute maximum and you will always find an absolute minimum. Alright, so we talked about the closed interval method. For a function that's continuous on a closed interval, the strategy was pretty simple. You knew that the absolute max and the absolute min would occur, and you had a pretty small list of points to check. You check them all, take the largest, take the smallest, done. Now it gets a little bit more challenging when talking about open intervals. But even though it's a little bit less methodical, and we'll see in the examples that there are just a lot of different weird things that can happen on open intervals, it's not quite as cut and dry, the strategy is more or less the same. Okay, so you want to find the critical points of f contained in the open interval. Okay, so you set f prime of x equal to 0. That's still step 1. Step 2 is still to evaluate the function at those critical points. Take the largest value and the smallest value. But now all you know is that those are candidates for being the absolute maximum or absolute minimum. Because you're on an open interval, the function can actually get larger than the largest value you found and smaller than the smallest value you found. And again, because you're on an open interval, you don't have endpoints to check. So you can't see, okay, well, the function is reaching a point at this endpoint and this endpoint, so either the largest value is in the middle or it's at the endpoints. So it's just kind of gets to the difference between closed intervals and open intervals. A function defined on a closed interval has to sort of reach all of its values, whereas on an open interval, you have limits as you approach the right and left endpoints, but you may not actually reach values out there. And in fact, you won't. You'll just be getting closer and closer and closer, and the function will never actually reach whatever value it's approaching. So step 3 accounts for this. We want to take the limit as x approaches a from the right and b from the left to see what the function is approaching. Then we use those values to either validate the functions or the values we found in part 2. So if one of the limits is larger than all of these values we found in part 2, there's no absolute maximum. And if one of these two values is smaller than all of these values we found in part 2, there's no minimum. Otherwise, the largest or smallest value found in part 2 is the absolute maximum or minimum. So the limits, as you approach the endpoints, basically all they're going to do is rule out whether or not you have an absolute maximum or absolute minimum. If they sort of stay within the range of values you found for your candidates at absolute maximum minima, then you will have an absolute maxima or absolute minima. And as I said, I think that just looking at several examples of this will kind of clarify all the different things that can happen. Okay, so here we go with the closed interval method. Notice, okay, we want to find absolute maximum and absolute minimum of this continuous function on this closed interval. So how we do this is pretty straightforward. We take the derivative, set it equal to 0. Well, first let's take the derivative, so that gives us 6x squared minus 6x. Okay, and we set it equal to 0 to find our critical points. So again, we're just finding the critical points. Okay, so let's do that. So this is a quadratic, so let's factor it. So we can factor out a 6x, and we're left with x minus 1. So either x is 0 or x is 1. So we have two critical points. And because we're on a closed interval, we know that the absolute max or absolute min is going to occur at x equals 0, x equals 1, or x equals 2. So we test the endpoints and the critical points. And notice something sort of coincidental happened here that happens from time to time, and that's that one of the critical points actually coincides with one of the endpoints. And that's perfectly fine, no big deal. But we want to evaluate f of 0, f of 1, and f of 2. Okay, so f of 0 is equal to 0. F of 1 is equal to negative 1. And f of 2 is equal to 4. So you look at this list. Here's the smallest value. Here's the largest value. So negative 1 is the absolute min, and 4 is the absolute max. And now, we weren't asked this, but just to review, the absolute min is negative 1. It occurs at x equals 1. The absolute max is 4. It occurs at x equals 2. So that's how it goes for the closed interval method. Take the derivative, set it equal to 0, find the critical points, test the endpoints and the critical points. Largest is the absolute max, smallest is the absolute min. Okay, so another continuous function defined on a closed interval. So we apply the closed interval method. First step is always just to take the derivative. In fact, you'll find in calculus, 9 times out of 10, if you have a function, you have to take the derivative. So you might as well just, if you don't know what else to do, just take a derivative, right? That's probably the easiest part of this class at this point. Once you learn the differentiation rules, just do it. So what's the derivative here? Well, we got to use the power rule. So we'll bring down the 2/3. 3 times 2/3 is 2. And then we have x to the, okay, so subtract 1 from 2/3, we have minus 1/3. And then plus 0. The derivative of 1 is 0. And now if we set f prime equal to 0, well, there are no solutions, right? So the 2 times x to the negative 1/3 is 2 over x to the minus 1/3. No, sorry, x to the positive 1/3. So this has no solutions. But does that mean we have no critical points? Well, no, because recall that a critical point wasn't just when the derivative was 0. It could also be when the derivative is undefined. So f prime is undefined when x equals 0. And another important note is that 0 is in the domain of f. So a critical point isn't just where the derivative is undefined, it's actually where the derivative is undefined and the original function is defined. Because if the original function isn't defined there, well then the function isn't continuous. So there's a problem, right? We can't even use the closed interval method. Okay, so f prime is undefined when x is 0. So the point is, we have one critical point at x equals 0. So CP for critical point. Now we just test. We test the critical point and the two endpoints. So we have f of negative 1. What is f of negative 1? I got it right here. I mean, you can just plug it in. Looks like it is 4. Looks right. And then f of 0 is 1. And then f of 8 is what? Looks like 13. Okay, yeah, because 8 to the 2/3 is 4. 3 times 4 is 12 plus 1, 13. Yep. So here we go. Here's our absolute max. We just picked the largest value out of this list. And then here is our absolute min. And that's how it goes. Pretty straightforward with the closed interval method. Alrighty, so sine of x is a continuous function. This is a closed interval from 0 to pi. Let's do it. Closed interval method. First things first, take the derivative. F prime of x is cosine of x. There's not going to be any points where cosine of x is undefined. The domain of cosine is all real numbers. But if we set f prime equal to 0, well, we want to set cosine of x equal to 0. And well, this is a little tricky because there are actually infinitely many x values for which cosine of x is equal to 0. So specifically, this is going to be 0 when x is something like this. So 2n plus 1 over 2 times pi, where n is just any integer, okay? But the whole point of this is, of course, that we're in a closed interval. So how many of these infinitely many x values that make cosine of x equal to 0 are actually contained in the interval from 0 to pi? Well, only one. right? So we're looking for the critical points that are contained in the closed interval. And so the only kind of odd or half multiple of pi contained in the interval from 0 to pi is pi over 2. So x equals pi over 2 is the only critical point. Okay, so this was just kind of a mess. Maybe I even regret writing this, but I mean, the point is the only x value for which cosine of x is equal to 0 in the interval from 0 to pi is pi over 2. And if you don't believe me, just look at the unit circle. Okay, so you're looking for an angle between 0 and pi for which the x coordinate on the unit circle is 0. Well, that's only going to be 90 degrees, pi over 2. So now let's look at f of 0, which is 0. Sine of 0 is 0. F of pi over 2, so this was the left endpoint, this is the critical point, is 1. And then f of pi is 0 again. So this is pretty easy. We just want to take the min and the max of this finite list. So this is the absolute max. But we probably already knew that, just based on the properties of sine. Okay, so and this is the absolute min. And notice that the absolute min actually occurs at two x values, so x equals 0 and x equals pi, but that doesn't really matter because we're just trying to find the absolute max and the absolute min. Absolute max is 1, absolute min is 0. Okay, another function, e to the x. This is a continuous function over its whole domain, so it's going to be continuous on the closed interval 0, 1. That means we have an absolute max and absolute min. First step is to find the critical points. So we set f prime equal to 0, but f prime of x is just e to the x. So if we want f prime to be 0, we just want e to the x to be 0. And so I want to review a very key fact here. Now, some of you may have already thought of this, but how do we solve this equation? Well, there are no solutions. And that's coming from a very important fact that we mentioned when we reviewed pre-calculus. But the key fact is that e to the x is always positive. And this is going to be so important for the rest of this topic, because we're going to be wanting to know when are things positive and when are things negative. Well, if we ever see an e to the something, we can basically just ignore it because it's always positive. It's never going to be 0 and it's never going to be negative. Therefore, no critical points. And here, there really are no critical points because also e to the x is never undefined. Okay, so there's no critical points. But that's super cool because then that means that the function attains its absolute max and min just at the boundary. Or in other words, the function is either always increasing or always decreasing over this interval. But I think I'm getting ahead of myself. For now, all we need to do is just test the x values that are the critical points and the endpoints. We have no critical points, so we just test the endpoints. Okay, so f of 0, e to the 0 is 1, and then e to the first is just e, so we're done. And recall that e is like 2.7 something. So this is the absolute min. Of course, it's important. I mean, we need to compare these values, right? We need to take the larger the value to be the max. So it's important to know that e is about 2.7. So specifically, it's bigger than 1. So that means that f of 1, which is e, is the absolute max. And that is that. Okay, so we're going to switch over to talking about the open interval method and different examples of that. So the caveat here, we still want to find the absolute maximum and absolute minimum, but we need to understand that they may not exist, right? So the extreme value theorem is not going to apply, even though this function is continuous on this open interval. It still may not have an absolute maximum or an absolute minimum. But the first step is the same. Take the derivative. So what is the derivative? Well, it's 2 times x minus 1. So to find the critical points, we'll set f prime to be 0, or 2 times x minus 1 to be 0. But the only way this is 0 is if x is equal to 1. So here's our one critical point. And again, notice the derivative is always defined, so we don't have any critical points coming from the derivative being undefined. So what we want to do is you just want to evaluate the function at all of the critical points. So in this case, we get 0. So 0 is potentially the absolute max and the absolute min. The only way it's not one of those two things is if we get messed up when we take the limit to the endpoints. So we need to next evaluate, this is step 3, the limit is x approaches 0 from the right, and the limit is x approaches infinity. I mean from the left, but you're always approaching positive infinity from the left. Okay, so we just take the limit as we approach these two endpoints from within the interval. Okay? And so the limit is x approaches 0 from the right of f of x. Well, this is a continuous function, so we can just evaluate at 0. It's just going to be 1. Okay, well that already tells us that this can't be a maximum because we are approaching something larger than this value. Strictly larger than this value. Then the limit as x goes to infinity. Well, this is a quadratic polynomial, okay, and it has a positive leading coefficient. So just using our end behavior rules for polynomials, this is going to positive infinity. So definitely this is not going to be an absolute max. And actually, whenever we have the case of a function going off to infinity, this is a red flag that tells us there is no absolute max. But notice that neither one of these endpoints are going below 0. So they're both going above 0. So what that means is that actually f1, which is 0, is the absolute min. Okay, so the only way it wasn't the absolute min is if one of these limits was actually below 0, or it was negative. Okay, and the way this works is because you might say, well, how do I know it doesn't dip down below 0 as it's going off to infinity? But if it did that, it would have to change direction. So just think about the graph of this function. So we have that it's approaching 1, and then it goes down to 0. And of course, it's going off to infinity. But your question is, how do I know it doesn't dip down below and then go off to infinity? Well, because I know it eventually goes off to infinity, if it dipped down, it would have to have a turning point. And so that would be a point where the derivative would have to be 0 or it would have to be undefined. So we know this can't happen. And in fact, we know that this function is increasing indefinitely after x equals 1. So there is no absolute max, and this is indeed the absolute min. All right, so this is an interesting function, to say the least. It's going to be a little bit delicate to deal with, but at least we have a framework of how to evaluate this function and find its critical points, test the endpoints, even on an open interval, to find the absolute extrema, if they exist. So the first thing is to take the derivative. That's always true. So if all else fails, let's just take the derivative. Now, okay, this is a tricky derivative. We got to use the chain rule. So this is -2. The derivative of cosine is negative sine, so I'll make that positive. So sine of all of this mess times the derivative of this, which is, okay, it's going to be 2 pi, and then negative, so this is 4x plus 1 to the -1, so we bring down the -1, we're left with 4x plus 1 squared, and then we have another factor of 4, okay, and then okay, and then that's it, and then plus 0. Okay, so that's the derivative. So a little bit messy. Let's look at what's going on here. So first of all, notice that x is going to be between 0 and infinity. Okay, so sine here, we have 2 pi, 4x plus 1, okay, 0 infinity. So it looks like the only way we're going to have a critical point, so if we have f prime is 0, the only way this is going to be the case, because this is always, well, this is negative, that's positive, none of that's ever going to be 0. The only way this is going to be 0 is if sine of this guy is 0. But that's only going to happen if 2 pi over 4x plus 1 is a multiple of pi. Or in other words, if we just cancel the pi, we want 2 over 4x plus 1 to be an integer. Okay, so when is this the case? Right, so the only way sine is 0 is if the argument is a multiple of pi. The only way this is a multiple of pi is if 2 over 4x plus 1 is an integer. So when can this be the case? Well, this definitely, since x is between 0 and infinity, we are only thinking about this being a positive integer. Okay, so 1, 2, 3, etc. But now what that means is that 4x plus 1 in the denominator is always bigger than 1. So actually, 2 over 4x plus 1 for x between 0 and infinity is strictly between 2 and 0. Which means the only way it can be an integer is if it's equal to 1. So if I set 2 over 4x plus 1 equal to 1, I get x is equal to 1/4. So this is the only critical point. Okay, so you can see how these get a little bit tricky, especially when trig comes into play, but make sure that sort of makes sense. Okay, so we want this to be a multiple of pi. Okay, so we need this to be an integer, but just based on where x is, 4x plus 1 has to be bigger than 1. So that means that 2 over something bigger than 1 can't be bigger than 2, but it's also positive. And the only integer between 0 and 2 is 1, so that means the only solution I could have here is when this is equal to 1, but that happens exactly when x is 1/4, because 4 times 1/4 is 1, 1 plus 1 is 2, 2 over 2 equals 1. Okay, so what is f of 1/4? Now that we have our critical points, we just want to evaluate our critical points. Well, f of 1/4 is 3. And why is that? Because if I plug in 1/4, I get 2 over 2, so pi, so cosine of pi is -1. So -2 times -1 is 2, plus 1 is 3. So 3 is our only candidate to be a max or a min. The next thing we need to do is take the limits. So the limit is x approaches 0 from the right. But fortunately, this function is continuous at 0, so I can just plug in 0. That's going to give me cosine of 2 pi, right? 2 pi over 1, times -2. So cosine of 2 pi is 1, -2 plus 1. So this is -1. That rules out this being a absolute min, right? Because we have function values that are going to be smaller than 3. Then if we take the limit as x goes to infinity, well, let's think about this. If x goes to infinity, okay, cosine's continuous, so we can just take the limit of this first. So 4x plus 1 as x goes to infinity is going to get very big. So 2 pi over a very big number is getting very small. So this is approaching cosine of 0, which is 1. -2 times 1, -2 plus 1. So again, the limit as x goes to minus infinity is -1. So we ruled out the case that f of 1/4, which is 3, could be the absolute minimum, but actually, based on our end behavior as x goes to 0 and to infinity, the function's leveling off to -1, so this value must be larger than all other values. So this is the absolute max, and there is no absolute min. Okay, so that's sort of how it goes. Hopefully you're starting to get the hang of it. All right, so another function here, negative square root of x, defined on an open interval. So at this point you should know, first thing to do, without even thinking, is to take the derivative. So we can find the critical points, which are the candidates for the absolute max and absolute min. Okay, so hopefully at this point, square root of x, you know how to take the derivative of. And so if we set f prime to be 0, we want -1 over 2 root x to be 0. Now that does not have any solutions. A good way to think about that, if you have a fraction, the only way the fraction is 0 is if the numerator is 0. But of course -1 is never equal to 0. So this has no solutions. However, the denominator can be 0. So f prime is undefined when x is 0, but x equals 0 is not in our interval that we're considering. So we ignore. this critical point. But wait a second. This is as easy as it gets, right? So remember that for the open interval method, the absolute max or absolute min has to occur at a critical point inside the open interval. But if there are no critical points, this is so easy. There are no absolute max and no absolute min. No work to be done. I don't even need to take the limits and test the endpoints to rule out potential max and mins because there are no potential max and mins. And so later we'll see that that's because this function is either always increasing or always decreasing, or in other words, it's monotone. So because it's monotone, it doesn't have any local extrema, and so therefore it has no absolute extrema on an open interval. Okay, 1 over 1 plus x squared defined on the whole real line, which, just so we're all clear, this is minus infinity to infinity. So it really is an open interval. Alrighty, so first things first, take the derivative. When in doubt, just take a derivative. Maybe you'll get some partial credit. Okay, so this is a quotient. So we can also think about this in terms of the chain rule, but I'll just do the quotient rule. So this is low d high, so 1 plus x squared times 0 minus 1 times 2x all over 1 plus x squared squared. And so I know sometimes we're a little bit lax about simplifying when we take a derivative, but this is not the time to not simplify. Okay, you're trying to see when this derivative is equal to 0. Your best bet to see clearly when it's equal to 0 or when it's undefined is really to simplify. Okay, so this, of course, is 0. So we just have minus 2x over 1 plus x squared all squared. Notice that the denominator here is always positive, okay, because I'm taking 1, adding a positive number, and then squaring it. So that's definitely going to be, well, it's going to be strictly bigger than 1, so it's definitely going to be positive. So this derivative is never undefined, but it can be 0. And remember, the only way a fraction is 0 is if the numerator is 0. So we see that x equals 0 is a critical point. And so what is f of 0? It's 1. So we have exactly one candidate to be a max or a min, absolute max or absolute min. So we just need to test the end behavior to see if the limits to the right and to the left get larger or smaller than 1, and then we can rule it out. So the limit is x goes to infinity of f of x. Well, you can do a lot of work here, but you really don't need to. As x goes to infinity, so x gets really big, what's happening to x squared? It's even bigger. And then I add 1, it's even bigger. So this is just 1 over a big number. That's going to 0. And the exact same thing is happening as x goes to minus infinity. I'm squaring a big negative number, so it's a big positive number. I'm adding 1. So this is still 1 over a big positive number, so it's going to 0. But what that tells us is that this is not a minimum because our limits are smaller than this value. If they were larger, then this could be a maximum. But because either one of these limits is larger than the value at our critical point, we actually know that this is the absolute max. And we don't have any other candidates to be the absolute min, so there's no absolute min. The absolute max or min must be one of these at one of these. It must occur at one of these critical points, but there's only one, so there's no other critical points to be the absolute min. All right, one more example. This one's pretty cool. So again, we'll just remind you that the real line really is an open interval from minus infinity to infinity. This e to the x plus e to the minus x is actually related to the hyperbolic trig functions, which I'm not going to talk about. I mean, they're really not that mysterious. I mean, if you understand this function, then you understand, the idea behind the hyperbolic trig functions. But anyways, let's just do it. So we want to find the absolute max and absolute min. So the first thing to do is to take the derivative. And the derivative is e to the x plus the derivative of this is e to the minus x times negative 1 by the chain rule. So it's minus e to the minus x. Okay, that's good. So let's see. If we want f prime to be 0, notice f prime is never going to be undefined. If we want f prime to be 0, we basically just want e to the x to equal e to the minus x. Right, so we just want this to be 0, and we can just add over, etc. So I can multiply both sides by e to the x. Okay, and I have e to the 2x equals 1. Okay, so now how do I solve like an exponential equation like this? Well, I take the logarithm. So I take the log of e to the 2x, and it just becomes 2x. And then I take the logarithm here, log of 1, natural logarithm of 1, is 0. Okay, so these equations are equivalent. And we see x equals 0 is the critical point. So take natural log here, both sides. Okay, so we have one critical point. Let's evaluate the limits. Well, first let's evaluate f of 0, our potential max or min. E to the 0 plus e to the 0, that's just 1 plus 1, which is 2. And for the limits, the limit is x goes to infinity of f of x. Well, as x goes to infinity, e to the x is going to infinity, and e to the minus x is going to 0. We talked about this with in behavior of functions. So this is going to infinity. And then the same thing is happening as x goes to minus infinity. But this time e to the minus x is going to infinity, and e to the x is going to 0. Yep. So this is going to infinity. So because both of these are going to infinity, that rules out having an absolute max, so no absolute max. But it does not rule out this being the absolute min. So we do have an absolute min of 2, but no absolute max. And so that's the idea behind the closed interval method and the open interval method.